Okay, in this session, we want to really, all right, understand what is meant by random variable. You see this word occurring again and again in all of our subsequent discussions. You know, when you learn probability statistics, you cannot avoid this term, right? Random variable. And again, just like many terms that we have just discussed earlier on, we understand the word random, we understand the word variable, but random variable is rather different, and I need you to be on the guard, right? On your guard about how to internalize this concept here. And that's why I want to spend one little session on this and kind of juxtapose it. And I put it side by side with other ideas like this word distribution. You see this a lot, and you cannot really master the basics of statistics and probability if you don't understand this word, if you don't have a mental mechanism to think about it, right? We all understand the world in our own ways, uh, but I want to share with you maybe a very uh, what I think is convenient way that is likely to let a lot of people absorb this concept. Okay, so let's try and see. Random variable, right? So this is basically an abstract description of what we meant by a set of data. So it's too generic and it's too simple, and it therefore makes it even harder because it's so simple, right? So what is random variable? Well, think of it as a bag. It's a bag containing balls, a bag containing apples, right? And apples come with different sizes. And balls may come, if they're rubber balls, they may, or plastic balls, they may come with slightly different sizes because of manufacturing fluctuations and various things, right? So a bag of apples, a bag of balls, a set, a bag of data. And what about the apples? Well, the apples could be, we're interested in the weight of each apple. And for sure, it comes to your mind even if they're all harvested from at the same time from the same plantation, they will come with slightly different weights, right? One might be, I don't know, 50 grams, 120 grams, and 90 grams, and they will fluctuate quite a bit. Yeah. Or we're interested in the circumference of the apple, or top to bottom, So we can do plenty measurements, but those measurements, if you kind of like mentally discard the apples and just leave those numerical data as if they were printed on a card and a bag contains those cards, right? That would be a right way to think about random variable. So far, so good. Okay, so it's a bag of data, a bag of measurements. Now, I'm almost trying to, as if trying to make sure you know it by repeating more and more, right? That's possibly one way, but maybe when we put them together, it's easier to understand. So, first of all, what is distribution? A distribution, well, the English word is has got several meanings, and I'm not sure if it's helpful, right? Than if it has a very unique definitive meaning. Distribution doesn't necessarily mean here distributing things, the act of distributing things. Distribution here simply means that um, we are talking about the shape of this curve. Think of it as the outline, the silhouette when you shine the beam onto these bricks, and then this outline cast onto the wall, and we are talking about this outline. Is it sharp? Is it curved? Is it having few spikes or one spike? Does it extend to plus and minus infinity, or it starts from zero but extends to infinity? The shape of it, right? The layout of it is basically what distribution means. So the layout, of course, can be described mathematically. For example, if we have an outline that is going this way, and then stops, then we can call this an exponential distribution, and then stops here, right? Kind of modified this exponential distribution. If it goes up and then comes down and extends to plus minus infinity in the right way, as described by the relevant function, then we might call this a normal distribution, right? And maybe one more time, if it goes up to the middle and then it drops down like a pyramid, but it's a triangle on a 2D plane, then we might call this a triangular distribution. And one last one. If it is a rectangle, it's flat throughout, then we might call this the uniform distribution. Some of you already said it out loud, and that's great. Yeah. Okay. So basically, the outline is what we call distribution, and distribution is going to be the key thing. It's going to be the key thing to anchor our understanding. Therefore, knowing distribution well in any particular standard distributions, like uniform distribution, binomial distribution, Poisson distribution, right? So these are standard mathematical distributions that we will even spend one whole lesson on to talk about more in-depth way. What are these standard distributions that are commonly encountered, not only in daily lives, but also because of that in your exam and in your homeworks and in your exercises. So how do we understand them? Where do we apply them? And so on. So we will spend one whole lesson on it. But for now, let's understand the word distribution. All right, the outline of the various frequencies of the sample space. Now, random variable, we describe them as X in capital letters, Y, Z, W, right? We can use all the capital letters. Don't use small letters. So it's an international convention, so please follow that. So capital letters refer to random variable. Remember what's random variable? It is not like a dice. It's not random and actually not an algebraic variable like A equals to 1. Not like that. Okay, so it is basically a bag of data, right? But let me help you out. Think of it as a distribution. A bag of data is like the cards all jumbled up, right? But can we put the cards all laid up properly? Like an apple weighing 70 to 79 grams, how many apples are there that fall into this category? How many apples fall into this category? 80 to 89 grams, How many apples fall into this category, that category, and so on, right? They are non-overlapping, and these ranges of weights form our sample space. Remember the x-axis of the histogram? Yeah. So the x-axis, that is described individually as a range, but that's okay, no problem, because I can call this the light apple range, the slight heavier apple range, the medium apple range, we can call them with more meaningful descriptions, but it is a range. And distribution describes the y-axis more, the silhouette formed by the y-axis. Okay, so this one. Yeah, and what I try to emphasize here is think of them as one and the same. Is that okay? All right, so x, y, these are random variables, a little bit abstract. You can write them as if they were mathematical formulas and equations and all that. And so when you write it out, we start to lose sight of what they form, right? But we can anchor our understanding again by thinking, wait, x is a distribution, and distribution can be drawn as a histogram like this, where on a histogram we put frequency 5, 2 and 1 and 0, right? So that's our histogram, and this is our usual understanding of histogram. And distribution, typically we don't describe with the frequency. We divide by the total frequency to get numerical real numbers. Yeah, so we'll get something like, how many are there? 8, 9. So it's 1 over 9, 2 over 9, 5 over 9, 1 over 9. So that it adds up to 1. So, but that's just a little bit of a technicality, right? Because the shape between histogram and distribution has to be the same. Yeah, if there are 2 spikes, there'll be 2 spikes. If it's triangular, it's triangular. If it's rectangular, it's rectangular. So the shape won't change. Therefore, think of random variable as a histogram. Very important bridging concept for you. You need to think of it as this way. Very, very important. Now, I keep saying important, right? You might say, why? I know already it has to be like just another mind map kind of thing, right? Well, let's see. Now, remember, random variable, right? It's x and y. And it's very tempting because if you don't have a histogram next to you, just imagine seeing x and y. You might be thinking of, at some point, x plus 2. Yeah? X plus 2. How do you think of x plus 2? How do you think of x plus 2, right? Because in algebra, you might say, well, when x equals to 1, sorry about the writing, it's just hard, right? When x is 1, then x plus 2 is 3. But wait, x is not 1, you know. X is a bag of data, remember? Yeah, but the bag of data, I'm just imagining a bag of randomly tossed data cards with measurements on it. And then you're stuck, right? And then we don't know how to continue. So this is where I say, wait, don't be tempted to add it the way we add algebraic variables. That's a small little x. This is a capital X, right? Think of it this way. Try to write it down like this. X is a histogram, remember, right? So it is a distribution, therefore it's a graph. And now we are more grounded. Yes, we are stuck now because we are asking, well, how do you add 2 to a graph, isn't it? Yeah. But what is good, however, is that we are now being forced to think of the problem x plus 2 and what is the answer to x plus 2 in the proper way, by not just substituting x with, let me think, if x is 1, then it's 3. If x is 10, then it's 12. You know, that's not the right way. The right way is to think of it as a graph plus 2. And then we are very cautious now. Wait, how do I do that? Okay, now the plus 2 doesn't go to the y-axis. It goes to the x-axis, because remember, x is going to be our x-axis, the unique set of outcomes. So with the repetitions on the y-axis. So then what is going to happen is that if the center, let's say, is 10, then correctly we might think of it as when x is 10, when x is 10, it is 12. But how many times does 10 occur? Well, this much, right? This height, this much. And therefore, how many times will 12 occur? Of course, the same height. So basically, if you go through this point by point, then you find that, well, basically the curve has shifted, right, to the right by 2 units. So this becomes x plus 2.